calculate H. So let me remove this first. So we need to find expression for H under conditions when we do have information about both TS, TM, and T. So what is the way to calculate H? Yes.
I have a question about T at R equals R naught. Is that R equals 0 again, or is the second equation there, the second one down?
Here?
Yeah, what is that T at R equals R naught, or?
Yeah, so it is R equal to R naught because it's a sophist, right? So R equal to 0 is in the middle, right? R equal to R naught is at the external surface of the tube, right?
Your plane is in the center?
Yeah, I mean, it's always like this, right? So I mean, R goes from 0, which is in the middle, right? And R naught corresponds to, because we have to keep the symmetry, right?
Yeah.
So the line of the symmetry is in the middle of the tube, right? So that sketch was there, but then I removed. So any other concerns, guys? No concerns, right? So how to find H? If we have information about temperatures, and we know that Qs is constant, and it's given. So what would you use?
Flux is equal to H minus H open parentheses T minus TS. So for H.
Okay, yeah, so I have heard two different versions. Newton's law, maybe that's what you're telling about too, right? So Newton's law is what we can use, right? So because remember that whenever we start talking about H, the relationship between H and all other parameters is given by the Newton's law directly, right? Before we do anything else, think about Newton's law. Of course, we need to think about what we do for Qs double prime. So because Qs double prime is a quantity which is in principle can be found. We know that it's constant, but it might not be given. But we can always find it, right? So because we know that it can be written in terms of dt over dr for the liquid at I equal to R naught. Right, again, we use the same type of relation which we used already several times, right? So written for interface, again, so T here, is a T for the tube material or for the liquid? What do you think?
Liquid.
Liquid, right? So because for the tube we don't have any information, remember it, right? So which means that this K is not for the tube material, it is for the liquid. Right, we still can use it because it's at the surface of the solid, right? So that's why convection is reduced, and we can still use this Fourier law. Okay, so then we can rewrite it. We can say that H Ts minus Tm is equal to minus K C multiplied by 2 R over 4 minus 4 R in the third power divided by 16 R naught squared, taking at the position R naught. Or we can just, of course, substitute, and then we will get some value here. So what to do with Tm? So previously we said that we can define Tm. So Tm was defined in this way. So let me remind you the formula. So it's 2 over um R naught squared multiplied by the integral of u c r dr. Right, so this is just a definition for mean temperature inside of the tube. So previously we said that, okay, so distribution over u with respect to r is known, but for t, we don't have any expression, right? So we don't know dependence of t on r. So now we do have this expression, and we can calculate Tm so that we can actually get expression for h. Because Ts is expected to be given this will be just a constant when we substitute, right? And integral which we need to take is quite complex, so I don't want to spend time on long but not so difficult integral. But let me just indicate what it looks like. So you can take it at home if you like to check. So let me write what it will look like in general. Right? The Tm is equal to 2 over um r naught squared, integral between 0 and r naught. Inside I have 2 1 minus r over r naught squared. So in this case I'm substituting u by the known expression in terms of and r, multiplied by my solution for t, and I'm writing it in such a way that I will divide each term by r squared, r naught squared, to have terms in terms of r over r naught. So then I'm getting terms like 1 over 4 r over r naught squared minus 1 over 16 r over r naught in the fourth power minus 3 over 16 plus ts over c, capital C, r naught squared, r dr. So essentially, guys, I substituted my solution for t, but I divided each term by r naught squared, and then I have to multiply each term by r naught squared, right? And then since I have this capital C at the very beginning, I have to also divide ts, because remember my solution was for t minus ts. So now I have transferred ts to the right hand part. Okay? It's simple mathematics, but you will be able to follow it, right? If you want to check everything, but it's very simple procedures. So you see that integral is very long, but the advantage is that we can also divide here by r naught twice, and essentially introduce another r naught squared here to compensate for it. As a result, I can say that my integral changes to the integral between 0 and 1, where I have some function over y dy, right? And this function will be, my new y is r over r naught, right? Because I have this y squared, just y dy, it is y in the fourth power and so on, right? So essentially I can simplify this integral by using dimensionless r. Right? So I got dimensionless r by dividing by r naught, which is the only characteristic we still have for r. Right? So I'm taking this integral, but I don't want to show the details because it will take us quite a long time. So let me just show you the answer you can check. Tm is a function of x is ts minus 2 divided by alpha, which will come if we substitute all the constants we have inside. So in particular, constant s, c, sorry, qs double prime multiplied by 2 pi r naught over m dot cp, which is coming from capital C, multiplied by 3 r naught squared over 16. And then we should get for h just a constant, which is 48 over 11 k over 2 r naught. So book uses d, right? That's why I'm writing here 2 r naught in such a way, so that you recognize that it's the same as what book gives you, because 2 r naught is equal to d, which is also used by the book, which is diameter of the channel. So what is remarkable here is that h is just a constant. Is it any surprise to us? No, right? So because we have shown previously that for thermally fully developed, it should be constant, and it is constant, right? And we could get this constant by solving the problem. So what happens if instead of QS constant, we have done everything, all of it, right? So for QS constant. So what if instead of QS constant, we have TS constant? We know that both cannot happen. So the problem becomes more difficult because we cannot solve it analytically. But let me at least write the equation just to show what kind of equation we will get. Let me again write equation before simplifications. So I'm just writing this equation again. And if instead of QS I say that TS is constant, then I cannot replace dt over dx by dtm over dx, which I have done before, right? And then it was constant. Instead, I have to say that dt over dx is equal to ts minus t over ts minus tm. dtm over dx. Well, you will ask me, is it really simplification? I would say yes, because what I see here is that t is now not in the derivative, it's just t, right? And we don't have derivative with respect to x, we have only with respect to r, right? And then t itself. dtm over dx can be only a function of x. It cannot be a function of r, right? Ts is constant, and Tm can be a function of x only. It cannot be a function of r. So it is a simplification, but as you can see, we cannot really solve it analytically. So it can be solved by iteration procedure. Essentially numerically. And then if we do it, so for Nusselt number, which is h multiplied by d over k, we will get constant, which is 3.66. And by the way, so for this case, we will also define Nusselt number in the same way. So it is h d over k. In this case, it will be also just a number, but somewhat larger, right? So because k here will cancel, and d will cancel. I mean, d is just 2 are not. So we have 436 for QS constant, and 366 for TS constant.
I have a quick question.
Yes.
On that board over there, you said that you divided by, what did you divide by? R naught squared?
No, by R naught, everything, right? So, well, essentially here I divided it several times, right? So my solution, which I have developed, I divided by R naught squared, right? So each term by R naught squared, each term by R naught squared, this term by R naught squared, this term by R naught squared, for each of them, right? And I also multiplied by R naught squared here to compensate for it, right?
Okay.
So the second thing I did later, right? I divided this R by R naught and this R by R naught, right? As a result, I introduced another R naught squared. Okay, so twice. So now I have advantage of using a different variable, which is R over R naught, right? Then my range of integration changes from between 0 and R naught to 0 and 1, right?
Okay.
Which I have written, right? And this function is everything inside of the integral, and this dy is just d R over R naught. Okay? That's what I did. But in principle, in mathematics, you might say, well, why do it, right? So I just take the integral as it is, and you can do it, right? Whether it's more convenient or not, it's your choice, right? So I just prefer to do it in terms of dimensionless variables. Okay, guys, so any questions? Let's have some questions, and then we have one problem to discuss. So one simple problem, which will be example, like in the book. So any questions at this
Is there pages for that? Is there pages for
Yes,
this?
so thank you for asking. There are pages for this, yes.
I need to read that.
So the pages for this I gave you already last time, but I can
Okay.
repeat them, right? So pages, internal flow, right? So some pages for internal flow. So pages 5:18 to 5:39, right? So remember, last class meeting we started discussing it, but we did not finish, and that's why pages remain the same, right? I just give them usually once, but if you forgot, I can always remind you. So any questions, guys? Any questions? If there are no questions, let's see how we can solve some problems which are much simpler, right? So like problems which I can give you as homework problems or also exam or quiz problems. So examples. So example 1. We will discuss several examples. So again, we have a cube, and in this case, it's known that QS double prime is some constant A multiplied by X. So X goes along the cube and R goes in the direction of the wall. So the length of the tube is L. And we also have a knot, which is radius. So if we summarize everything which is given, so what is also given is TMI, which is TM at the position x equal to 0. So given TMI, then QS at the surface double prime, which is AX. We have also mass flow rate M, which is constant, Cp, which is constant. And that's it for the things which are given. So we need to find, in this case, Tm as a function of x. So in terms of problem statements, some of you, not many people, right? So, but I think I remember a couple of comments saying that I have to define problem statement more clearly. So again, guys, so what I try to do, I discuss in words the problem statement, right? And then I give a summary like this: what is given, what we need to find. It's a good strategy to do a summary like this, because based on it, you immediately see what is given, what you need to find, right? It's an interpretation of the problem statement. Problem statements in the book can be quite complex, right? So I advise you to do this type of things, because sometimes you start solving the problem without even knowing what is this property that we need to find. Not quite knowing, right? But you start already writing something. So here I do give you some sort of interpretation of the problem statement. But again, I understand that problem statements are sometimes difficult to understand, so I encourage you to ask questions if something is not clear with respect to problem statement, because then you cannot proceed really, right? So what should we do? How should we start solving this problem? So already based on all your knowledge, it's not given that it's thermally fully developed. Can we say that it's thermally fully developed? No, right? So because there is no statement which would allow us to say it is thermally fully developed. No statement here.
We can do energy balance
We can do energy balance. Okay, for what?
for the entire. So
Right, so for macroscopic, so we probably would like to do it for some volume element, right? So, but which goes through the whole cross section, right? Like before. So somewhere we always do some